Hello, everyone. Welcome back. Today, we're going to be talking about alkyne reactions. And so, alkyne reactions, you're going to come to find, are very, very similar to the alkene reactions that we've talked about. But before getting into those, we actually need to talk a little bit about alkynes themselves. And so, we're going to start off with a little bit of terminology. Because unlike alkenes, where we had a lot of background beforehand from E1 and E2, we don't have much background with alkynes. So there's two different kinds of alkynes that we really focus on talking about. Those are these terminal alkynes, and then we also have internal alkynes. All right? And the differences between these are that the terminal alkynes are where you have the alkyne that is on the end of a chain. And then these internal alkynes are alkynes in the middle of a chain, right? And although this seems very not useful in terms of terminology, we're going to talk about why it is in just a second. Because you can imagine that an alkyne that looks like this here, this is what we would call a terminal alkyne, whereas this one over here would be an example of an internal alkyne. Right? One of the main differences between these two are that terminal alkynes have this little hydrogen on them. And this hydrogen is relatively important because these terminal alkynes are acidic. All right? And that acidity actually contributes to some of the reactions they can do. You can imagine if we take just a generic terminal alkyne, such as this one here with the hydrogen, you may remember from acid-base chemistry that if you toss this in with something like sodium amide or NaNH2 and THF, you'll end up seeing an acid-base reaction where the nitrogen will act as the base and it will deprotonate that position to give you a negative charge there, right, which is countered by the sodium, and then NH3. And looking at the favorability of this reaction, we would say that the alkyne, this was in your Lucky 13 pKa's, it has a pKa of 25, right? And then the NH3, which would be our conjugate acid, has a pKa of 35. So looking at this, it's no surprise to say that this reaction is favorable in the equilibrium points to the right. And the reason this pKa is so low is because if you think about what we're getting in our conjugate base, all it is sp hybridization. So this right here is acidic due to the sp hybridization. Okay? And why this matters is because these terminal alkynyl anions, right? That's what this guy is right here. This is a relatively strong nucleophile. As a matter of fact, it's relatively good to the point that it can do the same reactions that strong nucleophiles can do. So, for example, if we were to take this strong nucleophile and add it into something like, let's say, a primary alkyl halide that is a good leaving group, it can actually do this reaction because just like other strong nucleophiles, it can perform something like an SN2, right? So the SN2 reaction here would result in the alkyne doing a backside attack and adding on those carbons, right? We can take a look at the mechanism down here where our alkyne is going to come in for this primary leaving group. And keep in mind, in this case, it does need to be primary because as we move towards these secondary and tertiary leaving groups, SN2 is going to be much less likely. But on this primary leaving group. It can come in, do that backside attack, and we end up kicking out the iodide in exchange for that nice new bond to the alkyne. But this isn't the only thing that it can do, right? Another thing that it can do is if it comes in and interacts with an epoxide, what we'll see happen is essentially it will once again do an SN2-like attack. This time, if we were to then follow this up with HCl and H2O, we would see we make an alcohol, right? And of course, this comes through in a basic epoxide ring opening where our alkyne is acting as our nucleophile. And then remember, for basic epoxide ring openings, it always attacks the less substituted side of the epoxide. And so upon doing so, it opens up the epoxide, makes that oxygen anion, which then upon reaction with HCl and water just goes through acid base to give us the alcohol. All right. So that's another good reaction it can do. One other one that it can do that most nucleophiles cannot is it can actually act as a Grignard, right? So let's say we added into this aldehyde with HCl and H2O. What we're going to end up seeing is it acts just like a Grignard reaction, where it adds in and you finish up with an alcohol. So this would be the addition to carbonyls. And the reason that it's so good at adding to these things is because it always forms these strong carbon-carbon bonds, right? And as we know, carbon-carbon bonds are very strong and really not reversible because you can't kick out a carbon as a leaving group, right? So once you reach this oxyanion, right, where that oxygen has this negative charge, it can no longer collapse back down to remake a double bond like we saw with many of the other carbonyl reactions. So instead, it's just stuck there until HCl H2O workup, upon which it makes the alcohol. So needless to say, terminal alkynes act as strong nucleophiles if they are deprotonated. So those would be terminal alkynyl anions. Now, that in mind, the reason that we bring up this difference between terminal alkynes and internal alkynes is because these terminal alkynes are the only ones that can do that because they're the only ones that have that acidic proton. All right, so internal alkynes can never be made into strong nucleophiles. They're just always weak. So with this in mind, the question now becomes, how do we actually make these types of alkynes, right? Because essentially, with our alkenes, we talked about how to make them. So now we really do need to talk about forming different types of alkynes. So with this, the first thing that you need to know is that E2 is necessary to form alkynes, right? The only other way that we can really form an alkyne is if we brought it in from another molecule and did a substitution like we saw in these three previous examples. But in terms of forming alkynes directly from something else, we got to do E2. And as a matter of fact, that E2 has to come from a dihalide, right? And so the dihalide is necessary because we need to essentially do two back-to-back eliminations. So what's it going to look like? Well, let's say we have this reagent here, right? This 2,3-dibromopropane. If we take this and we throw in sodium amide, NaNH2, we will need three equivalents in order to make an alkyne. But as a matter of fact, we'll actually end up making the deprotonated terminal alkyne in this example. That, of course, will have its sodium counterion. And then from here, if you give it some HCl, and H2O is a workup, you will protonate it and you'll have your terminal alkyne. But how does this reaction actually work? Well, let's take a look at the mechanism. Because this mechanism is not something that you have not seen before. We actually did have a little bit of a discussion about this when we were talking about E2 in the past. So, how this works is from our starting material, we have the negatively charged nitrogen act as a base. It's going to come around, it's going to perform an E2 by deprotonating this proton, which will then form the double bond between the carbons and kick out the leaving group all at the same time. All right. And so it doesn't matter which one does this first. Either way, one will do it, and then the other one will follow. Because once we've done this, we have essentially generated a situation where now we have this bromine on an alkene. Now, from here, we talked a little bit about how E2 needs that anti-paraplanar hydrogen. And in E2, this is the only one that can actually get that leaving group to leave. So at this point, another equivalent of the NH2 minus is going to come around, grab that proton, form the alkene, and kick out the bromide. At this point, we have generated our terminal alkyne. But the thing is, NH2 minus is also a strong enough base to deprotonate this terminal alkyne, which ends up generating our negatively charged sodiated terminal alkyne. Now, thinking about this, the question becomes, why would we need three equivalents? Because it looks like the last equivalent, all it does is generate that negative charge, which isn't even what we're looking for. But if you think about this kinetically, it makes a little more sense, right? The first step is an E2, right? This step is going to be pretty neutral in terms of speed, but we're going to call it, average in terms of its rate. The second step, though, this E2 goes through kicking out an sp2 hybridized carbon bromide bond, which, as we know, is very slow, right? Because just like in all of our other SN1, SN2, and E1 reactions, we can't really get rid of sp2 hybridized leaving groups. Only E2 can. And that's just because of how high energy it is. But that being said, this step is very slow. The final step, on the other hand, is just acid-base chemistry. This is very fast. And so if we look at this in terms of energy, what we see is our reaction starts out at a relatively high energy level because we have those NH2 minuses, right? Those are our reactants. We go through and we do the first step, which is an E2, right? And that generates our sp2 hybridized bromide. The second E2 is slower. So what that means is that the peak of energy needs to be higher than that of our original. So it must be all the way up here. But the thing is, by doing the elimination, we're also making that NH bond, which is a little more stable. So we do go down to a lower energy enthalpically, but in terms of kinetics, this is our rate determining step. And as we can see, it has massive activation energy. But then following this, now that we have that alkyne there, the next thing that happens is an acid-base chemistry step. And as we know, acid-base chemistry is one of the fastest reactions. So it has relatively no activation energy. This is super fast. So why does this mean we need a third equivalent? Well, if you think about it, we are essentially going through and we're not just working with a single molecule at a time, right? There are multiple different molecules in solution that are all going through this reaction scheme at the same time. So if we start out with 100 of the starting materials, we're going to end up sitting in a situation where some of them get over that first hill, and then they end up in this position that they have to get over that huge second hill. And if they do, once they get over that second hill, That acid-base reaction is so fast, it occurs faster than the other two reactions prior to it. And so what that means is if anything gets to that alkyne at a different time than any other molecule in solution, it's going to get deprotonated and use up one of those NH2 minuses. And so essentially the third equivalent just makes sure that everything reaches the same point, which is the far right-hand molecule, rather than some things getting stuck in between. So essentially we need a third equivalent of the NH2 minus to ensure nothing stops at this step, which energetically is in the middle of two huge mountains, right? So if we're making terminal alkynes, we need to make sure that we're always using a strong base and we always need three equivalents of it, okay? But that's really not the only way that we can do this, because keep in mind that's for terminal alkynes, right? What about internal alkynes? Well, these are a bit more simple because these follow the general principles that you would expect. Say that you have something that looks like this, and you run it through and you just add two equivalents of sodium amide. Well, what you'll end up seeing is that we do indeed just make the alkyne, right? Because essentially, if there's no spot for this to get deprotonated in terms of having no acidic hydrogen, there's no need for more equivalents. So there's no need for 3EQ due to the lack of an acidic H. Okay. Now then, one other thing that we have to keep in mind is we can also have geminal dihalides to form alkynes as well. It's the exact same mechanism, but rather than having what is vicinal, where they're on two separate carbons, we have them geminal, where they are on the same carbon. So you can imagine that if we were to take something like this dihalide and use two equivalents of sodium amide, we would also end up forming an alkyne, right? And it runs by the same principle, where for both of these reactions, mechanistically, there's only one way that we can do an E2 that makes sense. And that is since we have such a small base, it has to go Zaitsev, right? So it has to go to the most stable alkene position, which is going to have to be this disubstituted alkene. And so the first elimination is always going to undergo to form that more stable alkene. And then from there, of course, once you've reached the point that you have that sp2 hybridized bromine, the only way to get something anti to it is to have that hydrogen on the other side of the alkene. And so from there, the amide comes in, does the E2, and forms the alkyne between those two carbons. So these are how you can make these internal and terminal alkynes. It's just through E2, which we've already talked about many times in the past. So far in this lecture, we've covered a little bit of what is a lot of the previous reactions that we've talked about, right? SN2, epoxide ring openings, what is essentially a Grignard reaction. And then we've also covered E2 once again. So this is a reminder that these reactions never truly go away. We just repurpose them to show them slightly differently. All right. Now then, in terms of alkynes as nucleophiles, right? Because thinking about alkynes, they should also be able to act the exact same way that alkenes do. Right? When we think of alkynes and we think about what they look like, essentially, if we were to take a super simple alkyne, such as this one here, we can draw it the same way we did alkenes when we were doing our orbital drawings of the p orbitals that are related to these structures, right? We will have some p orbitals that are above and below the plane, right? Such as these two that are facing up and down. And of course, these have overlaps, and that creates one of our pi bonds. The other one is from these that are going in and out of the plane of the paper, right? And so we can draw those as a bit more like wedges and dashes. And so these overlap to make our other pi bond. And whenever you think about these, they act the exact same way as alkenes, where essentially they are made up of two electrons and thus have excess electron density. Therefore, we can also say that alkynes are nucleophilic. The question becomes, are they more or less nucleophilic than alkenes? And to answer that question, we kind of need to go through and think about what it means for these to be nucleophilic, right? So, looking at the bond strengths of these alkynes, what we see is, let's say we checked through and we did the BDEs for each of these alkynes, right? And we'll do it with an alkyne, an alkene, and an alkane, all right? And we're going to do it for the most simple of each of those. So for an alkyne, let's say we went through and we broke every single one of these bonds in the middle here, right? We just chopped them up. If we're thinking about this in terms of BDE, we would say that each of those bonds would come from breaking one electron to one carbon and the other one electron to the other carbon. So each one has three bonds that are being broken at the same time. The total BDE here happens to be 200 kilocalories per mole. All right. On the other hand, when we think about our alkenes, we didn't necessarily do this same analysis, but we're going to do it now. Looking at these, if we break it apart into two CH2s, we're only breaking two bonds. And so in that, only two electrons end up on both carbons like that. But the total bond dissociation energy for breaking all of these is 146 kcals per mole. Now, if we're looking at just a plain old carbon-carbon bond for sp3 single bonds, we would find that we're only breaking one bond here, so each carbon will only end up with one electron for our BDE. But we find that the total BDE here happens to be 83 kilocalories per mole. So, at first glance, looking at this, up at the very top with our alkynes, this has the highest overall bond strength. So theoretically, alkynes would be the least reactive. But what about strength per bond? Because remember, for the alkynes, we're breaking three bonds, unlike for the alkanes, we're breaking one, and alkenes, we're breaking two. And so starting from that lowest energy BDE in terms of the lowest total, looking at the CH3CH3, what we're actually breaking is that single sigma bond. And so our total BDE, which we had just written down as 83 kilocalories per mole, is also the BDE of our sigma bond. So our sigma bond BDE happens to also be 83 kilocalories per mole. If we take this same idea and then apply it to our alkene, what will we find? Well, we're breaking one sigma bond and one pi bond. So whenever we look at the total BDE here of being 146 kilocalories per mole, we can extrapolate the idea that last time we said that the sigma BDE happens to be 83 kilocalories per mole. And now with that idea in mind, we can figure out the actual energy of the pi bond. So the pi bond BDE in this case actually runs up to be 63 kilocalories per mole, right? Because that's just 146 minus the 83. So in reality, when we're talking about these pi bonds, the pi bond is far weaker than the sigma bond. All right. And then if we want to take that and apply it to an alkyne, we can see the difference between that and the alkene. Because in this case, when we're breaking these bonds, we're breaking one sigma bond and two pi bonds. So we would expect that the total bond association energy should be equal to two pi bonds and a sigma bond. But what we actually see is the total BDE ends up being 200 kcals per mole. But if we calculate this out and we assume that the numbers are the same from beforehand, which they are, we would say that the sigma BDE is 83 kcals per mole. We would say the pi bond for the first one, we'll call this pi 1 BDE, should be the same at 63 kcals per mole. But that difference between the 146 and 200 is not also 63. The second pi bond actually is only made up of 54 kilocalories per mole. So what does that tell us? It tells us it's actually easier to break that second pi bond. And so when looking at this value right here, we can say, despite having the highest overall BDE, alkynes have the weakest bond present, right? So by delta H, it's the easiest to break. So what this means for us is when we're looking at alkynes versus alkenes, it should be enthalpically favored for an alkyne to react faster than an alkene. The funny thing is, though, when delta G comes into play, that may not be entirely true. But we're going to start out by looking at situations where this is actually the case. Because the first reaction we're going to look at is hydrogenation. And so this was a reaction that we saw in alkene chemistry, right? We would take an alkene, we would introduce it to hydrogen, just H2, and palladium on carbon. And what we saw is we would end up with an alkane. And we said that when we did this, it is adding hydrogen and hydrogen, right? Just adding the H2 across the bond. Didn't matter if it was Markovnikov or anti-Markovnikov because it's both hydrogen. And we said it was a syn addition. Thing is, whenever we do this in alkynes, it also does the same type of reaction. All right. So essentially, whenever we were thinking about running these types of reactions in alkynes, unlike alkenes, alkynes can do it twice. So if you took an alkyne, added in two equivalents of hydrogen with palladium on carbon, you would end up forming an alkane, right? Because it can just add in twice. And so what this actually looks like, and as a reminder, you don't need to know the mechanism for the hydrogenation reduction, but for the first equivalent of H2 that comes in and reduces, it should make a syn addition onto the alkyne to give you a Z alkene. The second addition then is the one that takes that alkene and makes it into an alkane. So from the alkyne, we are essentially doing two reductions to get to the alkane. And now the first thing that you may think to yourself is what if we only wanted one, right? Because in this case, what we're saying is that alkynes usually react and form alkenes, which react under the same conditions. All right? So unlike alkenes, these things can just do things twice. So what if we only wanted one addition to occur? Well, essentially, this actually ends up being very difficult for something like a hydrogenation. Say we took that same alkyne, we came in and we did hydrogen, but we did one equivalent, and then palladium on carbon. Well, the one issue here is that this palladium on carbon is actually the one driving the chemistry. And so this reaction's hard to control because the palladium is highly reactive. So what we end up seeing for products is that we have alkyne, we end up with the Z alkenes, and we end up with the alkanes. Because some of the alkenes actually react fast enough that they end up forming the alkane. So essentially, this right here is just a mix of products because both can be reduced. And that's a problem if we want to end up only adding one. But this one guy came up with a really good idea. He said, if the palladium's acting as the problem here, what if we made it not as reactive so that it ends up only doing this one time? And so this is what we call poisoning the catalyst. So if you poison palladium, you can make this thing that was from the guy that we're talking about called Lindlar's catalyst. And this guy, Lindlar, came up with the idea of if you take an alkyne and you react it in the same way where you have hydrogen, but this time in with your palladium, you add calcium carbonate and lead acetate, you'll actually decrease the efficiency of the palladium to where now it only forms the Z alkene. And notice this is even under conditions that aren't just one equivalent of hydrogen. So how does this work? Well, these two things right here are what we call catalyst poisons. And what they do is they make it less favorable for the catalyst to hydrogenate alkenes due to their stronger pi bond. Right? And so essentially what we're taking advantage of is that that pi 1 BDE is 63 kcals per mole, and then our pi 2 is about 10 kcals less. And so since that pi 2 is less energetically favorable, this palladium catalyst actually ends up right in that middle region where it can hydrogenate the alkyne, but then it stops at the alkene because that pi bond is too strong. And so essentially, this idea of taking palladium with this calcium carbonate and the palladium acetate creates what we end up calling, and what we will be showing it as, Lindlar's catalyst. All right. So essentially, Lindlar's catalyst cannot hydrogenate alkenes. So it always forms these Z alkenes. All right. And to give an idea of exactly what this would look like in an actual reaction, you can imagine that if we have some really fancy alkyne, like this one here, and we perform a reaction on it that is a hydrogenation with Lindlar's catalyst, rather than us taking this through and fully making the alkane, we do a syn addition on the alkyne to where we add the hydrogen on the same side, and we end up forming the Z alkene. All right. So we are able to actually only hydrogenate one single time, and it reduces it from that alkane to the alkene. But keep in mind, this is always Z, right? What about the E alkene though? Because if it's always adding syn, it's not like we can get it to go to the other side. And that's where another type of reaction happens that takes advantage of this same idea, but it will actually give us E alkenes. And this is called a dissolving metal reduction. So the way the dissolving metal reduction works is it takes an alkyne and you add it into two equivalents of sodium metal and ammonia as a liquid at negative 33 degrees Celsius. And you end up generating from this the E alkene. So this one's a little bit fancier, right? And it is going to be important to understand the mechanism of this reaction. So for the mechanism here, it actually starts out with an interesting step that works with the sodium metal, right? Because essentially this Na with the zero up here is indicating that this is a pure metal. When it comes in contact with the solution, sodium really does not want to have its extra electron because you can think of it as it can get to the point where it is more of a noble gas configuration if it loses that electron, right? So, since it is in the first column of the periodic table, loses an electron, becomes a positive sodium, it's now in a noble gas configuration. This electron right here, this is the thing that does the chemistry with the alkene or alkyne, right? Because electrons just sitting around aren't very happy. As a matter of fact, it's something that you rarely ever see. This is one of the few reactions that we say just generates an electron. And so the electron is going to actually run into this alkyne and do some chemistry. First thing it's going to do is it is a single electron, so it's going to have a single-headed arrow just like radicals. If it comes in contact with this alkene or alkyne, sorry, it's going to end up wanting to pair up with another electron, right? Because essentially unpaired electrons are super unstable, so if you can end up giving another electron to it, it's going to be very happy. That means the other electron that's in this alkyne is going to go to the other carbon where this electron doesn't go. And unlike forming a bond, which is what we normally see with these reactions, we're kind of just forming an electron pair. And so what we end up seeing is we now have an alkene where we have this now negative charge on one carbon because the electron has paired up with one there. And then on the other carbon is a single electron. And this is actually where we end up getting our trans or E configuration because these electrons will rotate in order to get as far away from each other as possible. And so this anti-configuration is the best way for the radical and the negative charge to be on opposite sides from one another. From here, our NH3 that acts as the solvent is actually also acting as a source of hydrogen, right? Because we have generated a carbon with a negative charge, which is incredibly basic. And since it's incredibly basic, it's going to want to grab the most acidic proton. Well, the only even close to acidic proton is from the NH3. And of course, we're all well aware that making a negatively charged nitrogen isn't a good idea, but there's really not much else that this can do here. From this point, we've now added on one of the hydrogens. And now our alkene is actually locked in to being in this E configuration. The reason we need the second equivalent of the sodium is because we have this radical sitting around, and the leftover one electron can come over and form a pair with that single electron from the sodium. Right? So now we've used both equivalents of our electrons that came from the sodium. And we now have another negative charge, which is incredibly basic. Right? This is also a very strong base. And so if that's the case, we should still have some more NH3 around because it is, of course, our solvent. And so this will grab one of those protons, form another bond to hydrogen, and we have now generated our E alkene. Thing is, though, when looking at this structure right here is an alkene. And you may say to yourself, well, it only makes sense if this can now do the same type of reaction that the alkyne did. But essentially, we can't, right? You cannot react again with the alkene for the same reason as above. It's due to the more stable pi bond. So in reality, the reason that these reactions work so well and stop at these alkenes is because of that slightly stronger bond. Okay? So when we're looking at these hydrogenations, to make the Z-alkene, you have to use something like Lindlar's catalyst. But to make the E-alkene, you have to use this dissolving metal reduction. So sadly, a mechanism that was a reaction that was incredibly easy from alkenes ends up being about twice as hard with alkynes. All right? But this is not the only type of reaction alkynes can do. Just like with alkenes, they can do additions. But these additions are a little bit different. We would expect that the alkyne would react faster than the alkene, right? It has a more unstable second pi bond. But what we find is that alkynes are much slower than alkenes to perform addition reactions, but still has a weaker bond. And this is slightly confusing, right? If we think about these other reactions up here, they only work because of that weaker bond. But then down here, we're saying that alkyne additions are slower, even though they have this weaker bond. So let's go ahead and actually explore why this is the case. So when we're looking at our alkyne additions, we can compare these to alkene additions by thinking about what happens if we add in HX, right? In the case of alkenes, the alkene acts as a nucleophile. It comes in, it attacks, and we end up adding the proton and generating a secondary carbocation. But what happens with alkynes? Well, for an alkyne, what we end up seeing is on the exact same type of framework, so just a four carbon chain with the alkene or alkyne in the middle, adding in HX, the alkyne will grab the proton and it'll end up forming this carbocation. Now, this doesn't necessarily have a name by the previous classifications that we gave for substitutions of carbons, right? We would normally say that this is an sp2 hybridized carbocation. But what does that actually mean for an alkyne? So let's draw out what this looks like physically to understand the stabilization effects. Because remember that the secondary carbocation is stabilized by hyperconjugation. But now for this sp2 hybridized one, what we see is the two carbons that make up the alkene still have these p orbitals above or below the plane that end up having the electron density shared between them. But then for their other substituents, right, the carbon on the right ends up having just that CH3 and the H. The carbon on the left has another methyl, right, that CH3. But then in the position where the hydrogen would normally be, right, and we can even draw it as sort of dashed, is this position that has the carbocation, right? And so this right here is no longer aligned with multiple CH bonds. So there's not much hyperconjugation. But here's the thing. There is still this CH3 out here that can do some stabilization, right? It can put one of its hydrogens sort of in this dashed position, where now it can use the electrons from that orbital to do some hyperconjugation overlap and do a little donation to that orbital with the positive charge. So in reality, that positive charge, that carbocation, is closer to a primary carbocation in terms of stability, aka highly unstable. So this should begin to make a little bit of sense. What we're saying is energetically, yes, the alkyne has a weaker bond, but that doesn't contribute to everything that has to do with the reaction rate, right? Because if we decide to draw a energy diagram where in blue we have our alkyne, and then in red we have our alkene, and let's just assume these start out at relatively close distances where the alkyne is technically going to be higher in energy just due to the fact that it has weaker bonds. The intermediates that we form are going to have massive differences in energy, right? Where on the blue path, if we go all the way up here, it's because that carbocation is incredibly unstable compared to what is essentially a secondary carbocation. And that energy is also reflected in our difference in the activation energy. So this energy difference here is accounted for by the hyperconjugation stabilization. And it's the same way with the difference and activation energy here. So, with that being said, the difference in activation energy, though, is entirely due to the transition state, right? And if we think about what the transition state looks like on this graph here, we would say that the transition state looks more like products. And so if you want to take a look at how that activation energy looks very different for these, go back and watch the original Alkene lecture because we go through that in depth. But it has to do with the fact that the positive charge exists more on that carbon there. It's almost a full positive charge when the reaction's done. So the overall takeaway is that overall, alkynes can still react, but they react very slowly. If you think about why these can react, even though it's kind of like a primary carbocation, when something like SN1 can't, you have to think about what they're reacting with. They're reacting with very strong acids. And so the fact that you can neutralize the strong acid and leave it as whatever halogen with a negative charge, that's going to be a lot more stable than just leaving it out in solution. So, with that being said, one thing that you can keep in mind with this idea that alkenes react slowly is if we go through and we show an example of what happens if you have a molecule with both an alkene and an alkyne. Let's say we expose this molecule right here to one equivalent of HBr. What's going to happen? Well, we know that the alkene both is more favorable to react and is faster to react. It has a lower activation energy. So what we'll see happen is the Markovnikov addition of HBr will put that bromine on that secondary carbon there, and the alkyne will remain completely untouched. So essentially, the alkene reacts before the alkyne for these additions. All right? Now then, what do these additions actually look like, though, when we're adding into alkynes? Because it's great if we have both an alkene and an alkyne around, and we're looking at something like this, but what if it's just the alkyne? And so we're going to go through and we're going to talk about most of the same reactions that we did for alkenes, but now we're going to look at them in terms of alkynes. So let's do addition of HX to alkynes, also known as hydrohalogenation. Now, with alkynes, you actually end up in a situation where there are two outcomes to most of the reactions that we present, right? The first outcome is what happens if we add something with one equivalent. The second outcome is what happens if we add something with two equivalents. Because as a reminder, with alkynes, they can do things twice. So for this first one, if we add HX to an alkyne with one equivalent, what's it going to do? Well, it actually does end up adding the halogen on the more substituted position. So it's still a Markovnikov addition of HX. The same thing happens with two equivalents, but instead of having that alkene, we just add another equivalent of the HX, giving us a second halogen on the same carbon. So essentially what we're saying for these is the number of times X, which as a reminder is chlorine, bromine, or iodine, number of times that is added is based on equivalence. Okay? So looking at something like this terminal alkyne, the question is, what does the mechanism actually look like this for this though? The way this looks is essentially our alkyne is going to do what it was meant to do, and it's going to act as a nucleophile, grab that proton, kick out whatever the halogen is, and it's going to generate that carbocation. And as a reminder about this, the more substituted position is still more favorable for the carbocation. right? We know this because of a drawing that we just did up here, right? If this one side has more substitution, that carbocation can be stabilized a little bit by the hyperconjugation. So the hyperconjugation does provide us a little bit of stability here. From here, that halide that we kicked out can now come in, add on to that position where the carbocation lay, and that is our first equivalent of X. And so, of course, this structure right here is where we stop at one equivalent. But of course, we don't always stop at one equivalent. Instead, if there's a second equivalent, it just follows the same idea, where the alkene now acts as our nucleophile, grabs the proton, and we generate a carbocation on the more substituted position. From here, our halide comes in, does an addition to form the carbon halide bond, and now this is where we get at two equivalents. All right. So the interesting thing about these alkyne reactions that makes some of them very easy is that overall, this reaction is just hydrohalogenation twice. All right. That is with a terminal alkyne though. And the reason that I bring this up as a terminal is because most of these reactions really only work well with terminal alkynes, right? Because let's think for a second about what this reaction looks like if we did it on an internal alkyne. Unlike a lot of our alkenes, it's a lot harder to get these to where one side is more substituted than the other. So if we had an internal alkyne that looks like this, and we tossed in HBr, just one equivalent, what we're going to see is that there's two possible outcomes, because both sides of this will end up being the same substitution pattern. So in one case, we're going to end up where it adds onto the left side. In the other case, we're going to get it to where it adds onto the right. The other confusing thing about this is I keep showing these as syn additions, right, where the hydrogen and the bromine are added on the same side, but this isn't exactly the case either. It can be a mixture of these, which we're not going to get into because it's not important. The important part about this is that there are two possible outcomes, right? And you end up with these constitutional isomers that don't really mean much because you're not getting a single product out. And so essentially what this means is that usually these additions aren't performed on internal alkynes due to poor selectivity. That being said, sometimes selectivity doesn't matter, which we'll be talking a little bit about next time, but for the most part, internal alkynes are not very useful for these additions. So overall, what we've learned so far is a little bit about how alkynes work in terms of using them as nucleophiles for the terminal alkynes. All right, that was all the way up here. So we can do SN2, we can open epoxides, we can add to carbonyls. We also learned a little bit about making alkynes from E2 reactions, both terminal and internal alkynes. And then we learned how alkynes can act as nucleophiles for reductions and for this type of addition. Next time, we're going to get into a little bit of hydration of alkynes, which actually does change up how these reactions work a little bit, and they're going to introduce a new mechanism for us. But then the rest of alkyne chemistry is going to be relatively similar to what we've drawn today. So I'll see you next time when we talk about those hydrations.